The planet you're standing on right now has died and been reborn more times than you can imagine. 252 million years ago, Earth crossed a threshold so catastrophic that 9 out of every 10 species simply vanished. What came after wasn't recovery. It was reinvention. The Triassic period emerged from that apocalypse, and the creatures that rose to fill the silence were unlike anything that had come before. This wasn't the age of dinosaurs yet. Not really. This was something stranger, more experimental, more desperate. Life was figuring itself out again from scratch, and the results were terrifying. At the dawn of the Triassic, Earth resembled a planet-sized wound trying to heal. The supercontinent Pangaea stretched from pole to pole, a single massive landmass surrounded by the Panthalassa Ocean. There were no ice caps. No polar bears waiting at the ends of the Earth. Just endless desert sprawling across the interior, where temperatures could spike beyond what most modern animals could survive. The Permian-Triassic extinction had just torn through the biosphere like a cosmic eraser. Volcanic eruptions in what's now Siberia had pumped gigatons of carbon dioxide and sulfur into the atmosphere for hundreds of thousands of years. The oceans acidified. Oxygen levels plummeted. Even insects, those nearly indestructible survivors, were pushed to the brink. So when life finally crawled back, it did so cautiously. The early Triassic was a shadow of what had been. Ecosystems were simple, almost primitive. Small reptiles and amphibians dominated, not because they were superior, but because they were what remained. Lystrosaurus, a pig-sized herbivore with a turtle's beak, made up roughly 95% of land vertebrates. Imagine a world where nearly every animal you encounter is the same species. That's how depleted Earth had become. But survival has a way of breeding innovation. As carbon dioxide levels stayed elevated and the planet remained hot, something unexpected happened. Life didn't just recover. It exploded into forms that had never existed before. The Middle Triassic saw the emergence of entirely new body plans, new strategies, new predators. And among them were the archosaurs, the ruling reptiles that would dominate for the next 150 million years. These weren't the archosaurs you're picturing. Not yet. Early forms like Eupercuria were small, maybe a meter long, with long tails and sprawling limbs. But they had something critical, an ankle joint that allowed more efficient movement, a more upright stance. This wasn't just anatomy. It was potential. While archosaurs were finding their footing, another group was already thriving. The cynodonts, distant cousins of modern mammals, were diversifying rapidly. They had differentiated teeth, whiskers, possibly even fur. Some paleontologists believe they were warm-blooded, a massive advantage in the volatile Triassic climate. These creatures weren't dominant, but they were persistent, occupying niches that larger predators ignored. Then there were the temnospondyls, massive amphibians that refused to give up their aquatic dominance. Mastodonsaurus could reach lengths of 6 meters, with a skull alone stretching over a meter. These weren't the frogs and salamanders you know. They were apex predators in rivers and lakes, crushing prey with bone-shattering jaws. But the real story of the Triassic isn't about who survived. It's about what they became. By the late Triassic, the world had changed again. Pangaea was beginning to fracture, though it would take millions more years to fully split apart. Rainfall increased in some regions, turning barren deserts into lush forests of conifers, ferns, and cycads. With more vegetation came more herbivores. And with more herbivores came larger, more sophisticated predators. This is when the monsters arrived. Prehistoric stalked the landscape of what's now North America, a quadrupedal predator built like a crocodile but acting like a wolf. For meters long, with powerful jaws and serrated teeth, it was an apex hunter, perfectly adapted to ambush prey in forested environments. Prehistoric wasn't a dinosaur. It was a Rauisuchian, part of that broader archosaur family that was experimenting with dominance. And it wasn't alone. Saurosuchus prowled South America, even larger, reaching up to 9 meters. These creatures moved on all fours but could rear up on their hind legs when attacking, combining power with flexibility. Their skulls were massive, reinforced to withstand the stress of crushing bone. They were, in every functional sense, the top of the food chain. Here's the strange part. These apex predators weren't dinosaurs, and they weren't destined to become dinosaurs. They were a separate lineage, one that would eventually go extinct. But for tens of millions of years, they ruled. Dinosaurs during this time were smaller, less specialized, still figuring out their niche. They weren't the kings yet. They were the understudies. So what were the early dinosaurs doing? Eoraptor, one of the earliest known dinosaurs, was about the size of a dog. It lived in what's now Argentina around 231 million years ago. Eoraptor had a lightweight frame, grasping hands, and a diet that was probably omnivorous. It wasn't dominating anything. It was surviving, adapting, learning. Herrerasaurus was another early dinosaur, slightly larger, more predatory. It had a flexible jaw that allowed it to grip struggling prey, a feature that would become more refined in later theropods. But even Herrerasaurus wasn't at the top. It coexisted with much larger predators, avoiding direct competition by targeting smaller animals. What's fascinating is that dinosaurs during the Triassic weren't inevitable. There was no sign they'd eventually take over. They were one experiment among many. Crocodile relatives were larger, more successful. Mammal ancestors were more adaptable. Dinosaurs were just another group trying to make it work. Then something shifted. The late Triassic brought another wave of extinction, smaller than the Permian catastrophe but significant. Volcanic activity surged again, this time associated with the breakup of Pangaea. Climate became more unpredictable. Sea levels fluctuated wildly. And in that chaos, many of the dominant groups faltered. Rauisuchians began to decline. Large amphibians lost ground. But dinosaurs, with their more efficient respiratory systems, upright posture, and flexible diets, started expanding. Not overnight. Not in some dramatic takeover. Just slowly, persistently, filling gaps as other groups weakened. By the end of the Triassic, dinosaurs were no longer marginal. They were ascending. Plateosaurus appeared in the late Triassic, one of the first large herbivorous dinosaurs. It could reach lengths of up to 10 meters and weighed several tons. Plateosaurus was a prosauropod, a precursor to the giant sauropods that would later dominate the Jurassic. It moved on all fours but could rear up on its hind legs to reach high vegetation, a body plan that hinted at future gigantism. And then there was Coelophysis, a small, agile carnivore that hunted in packs. Fossil sites in New Mexico have revealed dozens of Coelophysis skeletons together, suggesting social behavior. These weren't solitary killers. They were coordinated, adaptable, capable of taking down prey much larger than themselves through cooperation. This is the pattern that defines the Triassic. Life wasn't dominated by a single strategy. It was a chaotic competition of body plans, metabolisms, and survival tactics. Every group had a chance. Every lineage was testing the limits of what was possible. But there's another layer to this story, one that's often overlooked. The Triassic wasn't just about land. The oceans were undergoing their own transformation. Marine reptiles exploded in diversity during this period. Ichthyosaurs, dolphin-like predators, evolved from land-dwelling ancestors and returned to the sea, developing streamlined bodies, powerful tails, and sharp teeth for catching fish. Some species grew to over 15 meters in length. They weren't fish. They were air-breathing reptiles that had fully committed to an aquatic lifestyle, a transition that happened remarkably fast in evolutionary terms. Nothosaurs patrolled coastal waters, smaller than ichthyosaurs but equally adapted. They had webbed feet, long necks, and needle-like teeth for snagging slippery prey. These creatures occupied the shallow marine environments, hunting in estuaries and lagoons where the boundary between land and sea blurred. And beneath them, in the deeper waters, placodonts grazed on shellfish. These bizarre reptiles had flat, crushing teeth designed to crack open mollusks. Some species developed turtle-like shells, armored protection against the increasing number of marine predators. The Triassic oceans were becoming crowded, competitive, and dangerous. Just like on land, the rules were being rewritten. Predators were getting faster. Prey was getting smarter. And every evolutionary innovation triggered a counter-response. This is what makes the Triassic so critical. It's not just a prelude to the age of dinosaurs. It's the laboratory where modern ecosystems were forged. The Triassic tested carnivory, herbivory, gigantism, pack hunting, marine adaptation, and dozens of other strategies. Most failed. A few succeeded. And those successes shaped everything that followed. And then it ended. Not gradually. Not through slow decline. The Triassic closed with another mass extinction around 201 million years ago, erasing roughly 70 to 80% of terrestrial species. Volcanic eruptions associated with the breakup of Pangaea released massive amounts of carbon dioxide. global temperatures spiked. Ocean acidification returned. Ecosystems that had stabilized after the Permian were shattered once more. The difference this time was what survived. Dinosaurs made it through. Most of their competitors did not. Rauisuchians vanished completely. Large amphibians were decimated. Many marine reptile lineages disappeared. When the dust settled, the playing field had been cleared. The Jurassic period began around 200 million years ago, and for the first time, dinosaurs weren't just participants. They were dominant. This is where the popular image of prehistory begins to take shape. Giant sauropods grazing on towering conifers. Massive predators stalking through dense forests. But the reality was more nuanced than the simplified picture we often see. The early Jurassic wasn't an instant explosion of giants. It was a gradual expansion. Dinosaurs diversified into nearly every terrestrial niche. Some became enormous. Others stayed small. Some hunted alone. Others moved in herds. The key advantage dinosaurs possessed was efficiency. Their upright stance meant less energy wasted on locomotion. Their respiratory systems, with air sacs that allowed continuous airflow through the lungs, provided more oxygen per breath than mammalian lungs could manage. This wasn't a minor edge. It was fundamental. It allowed dinosaurs to sustain activity levels that other groups couldn't match, especially at larger sizes. By the Middle Jurassic, sauropods had grown truly massive. Brachiosaurus stood over 13 meters tall and weighed as much as 50 tons. Its long neck allowed it to browse vegetation that no other herbivore could reach, creating a feeding strategy that minimized competition. Diplodocus stretched even longer, reaching lengths of up to 30 meters, though much of that was tail. These weren't clumsy, slow-moving creatures. Recent biomechanical studies suggest sauropods could move at reasonable speeds, and their tails functioned as effective defensive weapons. A full-force tail strike from a diplodocus could shatter bone. Predators had to adjust. Allosaurus emerged as one of the dominant carnivores of the late Jurassic. At around 9 meters long and weighing up to 2 tons, Allosaurus wasn't the largest predator ever, but it was built for efficiency. Sharp, serrated teeth designed to tear flesh. Powerful forelimbs with large claws. A skull structure that allowed it to deliver slashing bites rather than crushing ones. Fossil evidence shows Allosaurus targeted sauropods, despite the size difference. Bite marks on sauropod bones match Allosaurus teeth. Some researchers suggest pack hunting, though the evidence remains debated. What's clear is that Allosaurus didn't need to bring down a full-grown sauropod alone. Juveniles, sick individuals, or isolated stragglers would have been easier targets. One successful kill could feed a predator for weeks. But not every dinosaur followed the path toward gigantism. Compsognathus, a contemporary of Allosaurus, was chicken-sized. Fast, agile, likely warm-blooded or at least capable of maintaining elevated body temperatures. It hunted insects, small lizards, and early mammals. Compsognathus represents the other end of the spectrum. Size wasn't everything. Speed and adaptability mattered just as much. The Jurassic also saw the rise of stegosaurs. Stegosaurus itself, with its distinctive double row of plates along its back and spiked tail, has become one of the most recognizable dinosaurs. But those plates weren't armor. They were likely thermoregulatory structures, helping control body temperature through blood flow. The real defense was the tail. For long spikes arranged in a cluster, capable of being swung with devastating force. Fossil evidence shows at least one Allosaurus died from a Stegosaurus tail-wound, penetrated vertebrae. Fatal injury. This wasn't prey waiting passively to be eaten. This was a creature that could fight back effectively. Meanwhile, in the skies above, pterosaurs were diversifying. These weren't dinosaurs, but archosaurs, a related group that had taken a different evolutionary path. Pterosaurs ranged from sparrow-sized insectivores to massive gliders with wingspans exceeding 10 meters. Pteranodon, though technically from the later Cretaceous, represents the culmination of this lineage. But even in the Jurassic, pterosaurs like Rhamphorhynchus were highly successful. Long tails for stability, sharp teeth for catching fish, membranes stretched between elongated fingers forming wings. Flight had evolved independently multiple times in Earth's history, but pterosaurs were the first vertebrates to truly master it. And then there's Archaeopteryx. Discovered in Germany in 1861, Archaeopteryx is one of the most famous transitional fossils ever found. It had feathers, clearly visible in the fossil impressions. It had wings. But it also had teeth, claws on its wings, and a long bony tail. Was it a bird? Was it a dinosaur? The answer is both. Archaeopteryx represents the evolutionary bridge between non-avian dinosaurs and modern birds. It couldn't fly like a modern bird. Its flight muscles were weaker, its wings less refined. But it could glide, possibly flap for short bursts. And that was enough. Flight didn't emerge fully formed. It evolved incrementally, each small improvement providing a slight advantage. Archaeopteryx lived around 150 million years ago, in the late Jurassic. By that point, feathers had already been around for millions of years, originally evolving for insulation or display rather than flight. Flight was a secondary adaptation, a repurposing of existing structures. This pattern repeats throughout evolution. Features evolve for one reason, then get co-opted for another. Feathers for warmth became feathers for flight. Fins for stability became limbs for walking. Evolution doesn't plan ahead. It tinkers with what's already there. The Jurassic world wasn't static. Climates shifted. Sea levels rose and fell. Pangea continued breaking apart, creating new coastlines, new ocean currents, new weather patterns. As continents separated, populations became isolated. Species that once could migrate freely were now cut off. This drove further diversification. Different environments selected for different traits. Dinosaurs in what would become North America evolved differently from those in Europe, Africa, or Asia. By the end of the Jurassic, around 145 million years ago, the stage was set for an even more dramatic period. The Cretaceous was approaching, an era that would see dinosaurs reach their absolute peak in size, diversity, and ecological dominance. But it would also be their last. Before we get there, though, there's something else worth examining. While dinosaurs dominated the land and pterosaurs ruled the air, life in the oceans was undergoing its own revolution. Marine reptiles had filled nearly every aquatic niche. Ichthyosaurs continued their reign as fast-swimming predators. But they were joined by plesiosaurs, creatures with long necks, small heads, and 4 powerful flippers. Plesiosaurs weren't fast swimmers. They were ambush predators, using their necks to dart forward and snatch fish. Some species had necks longer than their bodies, an adaptation that seems almost absurd until you consider the hunting strategy. Slow approach, sudden strike. And then there were the pliosaurs, the short-necked relatives of plesiosaurs. These were the apex predators of the Jurassic seas. Liopleurodon, though often exaggerated in popular media, was still a formidable hunter. Estimates put it at around 7 meters long with a bite force comparable to modern saltwater crocodiles. It fed on large fish, other marine reptiles, and possibly even smaller plesiosaurs. The oceans were just as competitive as the land. Every advantage mattered. Every weakness was exploited. The Jurassic represents a peak in biological experimentation. Dinosaurs had proven their dominance on land. Pterosaurs owned the skies. Marine reptiles controlled the seas. Mammals still existed, but they were small, nocturnal, and largely irrelevant to the larger story unfolding around them. Yet those mammals were learning, evolving, waiting. The Jurassic ended not with a catastrophe, but with a transition. Climates continued shifting. New species emerged. Old ones faded. And as the Cretaceous began, the world entered the final act of the dinosaur era. The Cretaceous period began around 145 million years ago. It would last for 79 million years, making it the longest period of the Mesozoic era. And during that time, dinosaurs reached their absolute zenith. This wasn't just more of the same. The Cretaceous brought new families, new body plans, new extremes. Sauropods grew even larger. Theropods became more specialized. Herbivores developed unprecedented defenses. The arms race between predator and prey intensified to levels never seen before or since. One of the defining features of the Cretaceous was the rise of flowering plants. Angiosperms appeared around 130 million years ago and spread rapidly. Before this, the world was dominated by ferns, conifers, and cycads. Flowering plants changed everything. They grew faster, reproduced more efficiently, and offered new food sources. Herbivorous dinosaurs adapted. New species evolved specifically to exploit these plants. Hadrosaurs, the duck-billed dinosaurs, became incredibly diverse during this time. They had complex dental batteries, hundreds of tiny teeth packed together, perfect for grinding tough plant material. Some species developed elaborate crests on their heads, hollow structures that likely amplified sound. These weren't just for display. They were communication tools. Hadrosaurs lived in herds, and being able to signal across distances was crucial for survival. Ceratopsians also flourished. Triceratops is the most famous, but it was just one of many. These dinosaurs had massive frills and horns, features that served both defensive and social purposes. The frills weren't solid bone. They had large openings covered by skin, which reduced weight. This suggests they weren't purely defensive. Display mattered. Intimidation mattered. In a world full of predators, looking dangerous could be just as important as actually being dangerous. And the predators? They were more lethal than ever. Tyrannosaurus rex appeared late in the Cretaceous, around 68 million years ago. It's often called the ultimate predator, and for good reason. T. rex could grow up to 13 meters long and weigh over 8 tons. Its bite force has been estimated at over 12,000 pounds, strong enough to crush bone. But size wasn't its only advantage. Recent studies suggest T. rex had excellent vision, a keen sense of smell, and could move surprisingly fast for its size. Estimates range from 17 to 25 miles per hour. Not cheetah fast, but fast enough to run down most prey. T. rex also had tiny arms, a feature that's been mocked endlessly. But those arms weren't useless. They were heavily muscled and could lift several hundred pounds. Their function is still debated. Gripping prey during feeding, helping the animal stand after resting. We don't know for sure. What we do know is that T. rex didn't need them for hunting. Its jaws did all the work. Other theropods took different paths. Spinosaurus, living around 95 million years ago in what is now North Africa, was possibly the largest theropod ever. Some estimates put it at 15 meters long. It had a massive sail on its back, formed by elongated vertebrae. The purpose of this sail is still debated. Thermoregulation, display, fat storage, all are possible. But what's most striking about Spinosaurus is its lifestyle. Unlike most theropods, it was semi-aquatic. Its teeth were conical, better suited for catching fish than tearing flesh. Its nostrils were positioned high on its skull, allowing it to breathe while partially submerged. Fossil evidence suggests it spent significant time in water, hunting large fish and possibly smaller dinosaurs that came to drink. This adaptability is key. Dinosaurs weren't locked into rigid roles. They experimented. They adapted. They filled niches that hadn't existed before. The Cretaceous also saw the rise of the dromaeosaurs, the raptors. The Velociraptor is the most famous, though popular media gets it wrong. The real Velociraptor was about the size of a turkey, not the human-sized monster from movies. But it was still a formidable predator. It had a large sickle-shaped claw on each foot, used for gripping and slashing. Its arms were long and flexible, with three-fingered hands capable of grasping prey. And it likely hunted in packs, coordinating attacks on larger animals. This level of social behavior suggests intelligence, at least relative to other dinosaurs. Larger dromaeosaurs did exist. Deinonychus, discovered in Montana, was around 3 meters long and weighed up to 70 kilograms. Utahraptor was even bigger, possibly reaching 7 meters and weighing half a ton. These weren't just scavengers. They were active hunters, using speed, coordination, and those devastating claws to bring down prey. Meanwhile, in the skies, pterosaurs reached their largest sizes ever. Quetzalcoatlus, appearing in the late Cretaceous, had a wingspan of up to 11 meters. That's wider than most small planes. It likely weighed around 200 kilograms, though some estimates go higher. How did something that large fly? Its bones were hollow and incredibly light. Its wings were made of a flexible membrane stretched between elongated finger bones. It probably spent more time gliding than flapping, riding air currents like modern albatrosses. What did it eat? Fossil evidence suggests fish, small dinosaurs, and carrion. It may have stalked shorelines, using its long neck to probe for prey. The oceans, too, were dominated by giants. Mosasaurs have replaced earlier marine reptiles as the top predators. These weren't dinosaurs. They were marine lizards, relatives of modern monitor lizards. The largest species, Mosasaurus hoffmanii, could reach 17 meters long. They had powerful jaws lined with sharp teeth, adapted for gripping slippery prey. They fed on fish, sharks, sea turtles, and even other mosasaurs. Bite marks on fossils show they weren't gentle. They were aggressive, dominant hunters. But the Cretaceous wasn't just about size. It was about diversity. Ecosystems became more complex. Food webs deepened. Interactions between species became more nuanced. Herbivores developed better defenses. Predators developed better attacks. Plants evolved chemical defenses, tough leaves, and toxic compounds. Herbivores evolved better digestion, detoxification systems, and behavioral strategies. This is coevolution in action. Each side pushes the other to adapt. Neither can afford to stop. And through all of this, the continents continued drifting. By the late Cretaceous, the world looked more recognizable. South America and Africa were fully separated. India was an island continent, drifting northward toward Asia. North America and Europe were still connected intermittently by land bridges, but the Atlantic Ocean was widening. These geographic changes had biological consequences. Populations isolated on different continents evolved independently. South American dinosaurs looked different from Asian ones. African species had their own unique traits. This geographic isolation drove further diversification. climate during the Cretaceous was warmer than today. There were no polar ice caps. Sea levels were high, flooding low-lying areas and creating shallow inland seas. Forests extended into polar regions. Dinosaurs lived in Antarctica, which at the time was temperate, not frozen. This greenhouse climate was driven by high atmospheric carbon dioxide, likely from volcanic activity. The breakup of Pangaea created new volcanic zones, new mountain ranges, new sources of CO2. The planet was warmer, wetter, and more dynamic than at any point in the Mesozoic. But warmth doesn't mean stability. The Cretaceous experienced its own fluctuations. Ocean circulation patterns changed. Regional climates shifted. Sea levels rose and fell. These changes weren't catastrophic, but they were constant. Species had to adapt continuously. Those that couldn't went extinct. Turnover rates were high. New species appeared, old ones vanished. Evolution never stopped. Toward the end of the Cretaceous, around 70 million years ago, something else was happening. Volcanic activity was increasing. The Deccan Traps in what is now India began erupting, releasing massive amounts of lava and gas. These eruptions would continue for hundreds of thousands of years, pouring out enough lava to cover an area larger than France. The environmental impact was significant. Sulfur dioxide and carbon dioxide flooded the atmosphere. Temperatures fluctuated. Acid rain became common. Ecosystems were stressed. But they endured. Dinosaurs were still thriving. The fossil record from the latest Cretaceous shows no sign of decline. Diversity remained high. New species were still evolving. There was no slow fade, no gradual weakening. Right up until the end, dinosaurs were doing what they had always done. Adapting. Competing. Surviving. And then, 66 million years ago, everything changed. An asteroid roughly 10 kilometers in diameter struck what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear bombs. The immediate effects were apocalyptic. A shockwave flattened forests for hundreds of kilometers. Tsunamis hundreds of meters high swept across coastlines. Debris blasted into the atmosphere, then rained back down as molten rock, igniting global wildfires. Within hours, much of the planet was burning. But the real killer wasn't the immediate impact. It was what came after. Dust and ash filled the atmosphere, blocking out sunlight. Temperatures plummeted. Photosynthesis stopped. Plants died. Herbivores starved. Carnivores followed. This wasn't a quick extinction. It unfolded over months, years, possibly decades. The darkness lasted long enough to collapse food chains from the bottom up. By the time the skies cleared, 75% of all species were gone. Every non-avian dinosaur vanished. Pterosaurs disappeared. Mosasaurs went extinct. The Cretaceous ended not with a gradual decline, but with a single, catastrophic blow. Yet some things survived. Birds made it through. Small mammals endured. Crocodiles persisted. Turtles survived. These weren't random survivors. They shared traits that mattered when the world went dark. Small body size meant lower energy needs. Burrowing behavior provided shelter from temperature extremes. Omnivorous diets allowed flexibility when food chains collapsed. The ability to enter dormancy, to slow metabolism and wait out the crisis, proved invaluable. Birds survived because they were small, adaptable, and could fly to wherever resources remained. Mammals survived because they were already living in the margins, already adapted to scavenging, already capable of exploiting whatever was available. The extinction didn't choose the strongest. It chose the most flexible. In the immediate aftermath, Earth was unrecognizable. Forests were gone, replaced by ferns and pioneer plants that could colonize bare ground quickly. The fern spike, a layer of fern spores found in rock strata worldwide, marks this moment. It's a geological signature of devastation, a planet resetting itself from scratch. For perhaps 1 million years, ecosystems remained simple. Food webs were short. Biodiversity was low. The survivors spread out, filling niches left empty. Mammals, no longer constrained by dinosaur dominance, began to diversify. Within 10 million years, they had radiated into forms that would eventually lead to whales, bats, primates, ungulates. Birds did the same, splitting into lineages that would become songbirds, raptors, seabirds, flightless giants. Life didn't pause. It exploded into the vacuum. But this wasn't a return to what came before. The Mesozoic was over. The age of dinosaurs had ended. What followed was something entirely new. The Cenozoic era, the age of mammals, had begun. And with it came a different set of rules. Mammals didn't dominate immediately. For the first few million years of the Paleocene, they remained small. The largest mammals were about the size of modern dogs. But they were experimenting. Some became herbivores, developing teeth suited for grinding plants. Others became carnivores, refining hunting strategies. Still others took to the trees, developing grasping hands and forward-facing eyes. The evolutionary paths that would lead to modern biodiversity were being laid down in real time. By 55 million years ago, during the Eocene, mammals had grown larger. Forests have returned, denser and more complex than before. Flowering plants, which had begun their rise in the Cretaceous, now dominated. They brought with them insects, specifically pollinators, creating intricate relationships that reshaped ecosystems. Mammals adapted to these new forests. Primates evolved, moving through the canopy. Burly horses appeared, small forest dwellers nothing like their modern descendants. Whales began their transition from land to sea, a process documented in fossil sequences showing progressive adaptations. The planet was warm again, warmer than today. Palm trees grew in Alaska. crocodiles lived in the Arctic. This was the Paleocene-Eocene thermal maximum, a period of rapid warming driven by massive carbon release, possibly from volcanic activity or methane clathrates destabilizing on the ocean floor. Temperatures spiked by 5 to 8 degrees Celsius in just a few thousand years. Ecosystems shifted rapidly. Some species went extinct. Others migrated toward the poles. Mammals continued adapting, some growing larger to cope with heat stress, others becoming more specialized. Then the planet began to cool. Gradually at first, then more dramatically. By 34 million years ago, Antarctica had frozen over. Ice sheets formed at the poles for the first time since the Mesozoic. Ocean currents changed. Climate zones sharpened. Tropical forests retreated toward the equator. Grasslands began to spread. This cooling trend, driven by shifting continental positions and declining atmospheric CO2, fundamentally altered life on land. Forests gave way to open plains. Mammals that had thrived in dense vegetation now faced new challenges. Some adapted by becoming faster, developing long legs for running. Others grew larger, using size as defense against predators. Horses evolved from small forest browsers into larger grassland grazers. Their teeth changed, becoming taller and harder to withstand the abrasive silica in grass. Their legs lengthened, their bodies streamlined for speed. This wasn't random. It was direct adaptation to a changing environment. Predators evolved in response. Carnivores became faster, more coordinated, more efficient. Pack hunting emerged as a strategy. Canids, ancestors of modern wolves and dogs, began working together to bring down prey larger than themselves. Cats refined ambush tactics, developing retractable claws and powerful builds suited for explosive attacks. The grasslands became arenas of predator-prey dynamics more intense than anything in the forests. Meanwhile, other lineages took different paths. Elephants and their relatives grew massive, developing trunks, tusks, and complex social structures. Whales, now fully aquatic, diversified into filter feeders and toothed predators, dominating the oceans in ways no marine reptile ever had. Bats refined echolocation, becoming the only mammals capable of true flight. Each group found its niche, exploited it, and diversified. By 20 million years ago, the planet looked more familiar. Continents were approaching their modern positions. India had collided with Asia, forming the Himalayas. Africa was moving toward Europe. North and South America were still separated, but the gap was closing. These geographic changes continued to drive evolution. Species isolated on different continents evolved in isolation. South America, cut off from other land masses, developed its own unique fauna. Giant ground sloths, armadillo relatives the size of cars, terror birds, flightless predatory birds standing 3 meters tall. These were the dominant animals of South America for millions of years. Africa had its own distinct groups. Early elephants, hippos, giraffes. Asia had rhinos, giant apes, saber-toothed cats. North America had camels, horses, mastodons. Each continent was its own evolutionary laboratory. Then, about 3 million years ago, the Isthmus of Panama formed, connecting North and South America. Animals began moving between continents. The Great American Interchange had begun. North American predators, more efficient and aggressive, moved south. South American herbivores, unused to such pressure, declined. Many unique South American groups went extinct. Ground sloths and armadillos moved north, but most didn't last long. The exchange was asymmetrical. North American species generally outcompete their southern counterparts. This wasn't because they were inherently superior. They came from ecosystems with higher competition, more predators, more pressure. They were battle-tested. Around 2.5 million years ago, the Pleistocene began. Ice ages returned, not as permanent features but as cycles. Glaciers advanced and retreated in roughly 100,000-year intervals, driven by variations in Earth's orbit and axial tilt. During glacial periods, ice sheets covered much of North America, Europe, and Asia. Sea levels dropped as water locked into ice. Land bridges appeared, connecting continents. Animals migrated across these bridges, spreading into new territories. Mammoths moved from Africa into Eurasia, then across Beringia into North America. Humans would follow the same route tens of thousands of years later. During interglacials, the ice retreated. Forests returned to high latitudes. Sea levels rose, flooding coastlines and isolating populations. This constant cycling drove rapid evolution. Species adapted to cold climates during glacials, then had to adapt again when warmth returned. Those that couldn't keep up went extinct. Megafauna thrived during this time. Giant mammals dominated every continent. Mammoths, mastodons, giant ground sloths, saber-toothed cats, dire wolves, short-faced bears, giant beavers, enormous kangaroos in Australia, elephant birds in Madagascar. These weren't anomalies. They were the norm. Large body size was advantageous in fluctuating climates. It allowed for better heat retention during cold periods and longer fasting during resource scarcity. But size also made them vulnerable. They reproduced slowly, needed vast territories, and required large amounts of food. When conditions changed rapidly, they struggled. And then, something new appeared. A small bipedal primate, originating in Africa, began spreading across the globe. Humans didn't seem like much at first. They were weak compared to the megafauna, slow compared to predators, lacking any obvious physical advantages. But they had something else. Intelligence. Tool use. Language. Cooperation. These traits allowed humans to hunt animals far larger than themselves, to adapt to environments from tropical rainforests to Arctic tundra, to survive where other species couldn't. As humans spread, megafauna began disappearing. The pattern is striking. In Africa, where humans evolved gradually alongside large animals, megafauna persisted. Animals there had time to adapt to human hunting pressure. But in regions humans entered suddenly, extinctions followed quickly. Australia lost its giant kangaroos, wombats, and reptiles within a few thousand years of human arrival. The Americas saw similar losses. Mammoths, ground sloths, saber-toothed cats, all gone within millennia of humans crossing into the continent. The debate continues over how much humans contributed versus climate change, but the correlation is undeniable. Where humans went, giants fell. By 10,000 years ago, the Pleistocene was ending. The last ice age was retreating. Glaciers melted, sea levels rose, climate stabilized. And in this new, warmer world, humans did something unprecedented. They stopped moving. They settled. They began farming. Agriculture wasn't an invention. It was a necessity. As megafauna disappeared, hunting became harder. Reliable food sources vanished. Humans turned to plants, domesticating wheat, rice, maize. They domesticated animals too. Sheep, goats, cattle, pigs. These weren't random choices. They were species that could thrive near human settlements, that bred quickly, that provided consistent resources. Farming changed everything. It allowed populations to grow. It created surplus, which led to specialization. Not everyone had to hunt or gather. Some could build, some could craft, some could organize. Settlements became villages. Villages became cities. Cities became civilizations. And with civilization came new pressures. Humans began shaping the environment deliberately. Forests were cleared for farmland. Rivers were diverted for irrigation. Animals were hunted not just for survival but for trade. The planet, which had been shaped by geological and biological forces for billions of years, was now being reshaped by a single species. This brings us to the present. The Holocene, the epoch we've lived in for the past 10,000 years, has been remarkably stable. Temperatures haven't fluctuated wildly. Ice ages haven't returned. This stability allowed human civilization to flourish. But stability is ending. We're entering what scientists call the Anthropocene. A new geological epoch defined not by ice or heat, but by human impact. The evidence is everywhere. Carbon dioxide levels in the atmosphere are higher than they've been in 3 million years. Global temperatures are rising faster than at any point in the last 10,000 years. Species are going extinct at rates 1,000 times higher than the natural background rate. The oceans are warming, acidifying, losing oxygen. Ice sheets are melting. Sea levels are climbing. Weather patterns are destabilizing. This isn't speculation. It's measured, documented, undeniable. The question isn't whether humans are changing the planet. We are. The question is what happens next. Climate change gets framed as a future problem, but it's already here. We're living through it now. Arctic ice is vanishing. Permafrost, frozen for millennia, is thawing, releasing methane. Coral reefs, ecosystems that support a quarter of all marine life, are bleaching and dying. Forests are burning with increasing frequency and intensity. Droughts are lasting longer. Storms are growing stronger. These aren't isolated events. They're connected, part of a system pushed out of balance. And unlike past climate shifts that unfolded over thousands of years, this one is happening in decades. Species can't adapt that fast. Ecosystems can't adjust. We're conducting an experiment with no control group, no way to reverse course if things go wrong. The parallels to past mass extinctions are uncomfortable. The Permian extinction, the worst in Earth's history, was triggered by volcanic eruptions that released massive amounts of carbon dioxide. The oceans warmed, became acidic, lost oxygen. 90% of species died. Today, we're releasing carbon even faster than those ancient volcanoes. Not from lava, but from burning fossil fuels, coal, oil, gas. The difference? Volcanoes couldn't turn themselves off. We can. But we're not. Not fast enough, anyway. Emissions keep rising. Temperatures keep climbing. The longer we wait, the harder it becomes to stop. Some argue technology will save us. Carbon capture, geoengineering, solutions that sound promising in theory. But technology isn't magic. It requires energy, resources, time. And even if we develop these tools, deploying them at planetary scale is another challenge entirely. Others suggest adaptation. Humans are resilient, they say. We've survived ice ages, droughts, disasters. We'll figure it out. And maybe we will. But survival isn't the same as thriving. Civilizations have collapsed before when climates shifted. The Maya, the Akkadians, societies that seemed powerful until suddenly they weren't. They didn't have global supply chains, interconnected economies, cities housing millions. We do. Which makes us more vulnerable, not less. Agriculture, the foundation of civilization, depends on stable climate. Crops need predictable rainfall, consistent temperatures, healthy soil. As climates shift, growing seasons change. Droughts strike breadbasket regions. Floods destroy harvests. Pests and diseases spread to new areas. Food security becomes fragile. When food becomes scarce, people migrate. When people migrate, tensions rise. History shows what happens when resources dwindle. Conflict. War. Collapse. We're seeing early signs already. Droughts contributing to civil wars. Floods displacing millions. Fires forcing evacuations. This is just the beginning. If temperatures rise by 2, 3, 4 degrees, the disruptions will be far worse. The ocean tells its own story. It's absorbed 90% of the excess heat we've added to the system. That sounds helpful until you realize what it means. Warmer water expands, raising sea levels. Warmer water holds less oxygen, creating dead zones. Warmer water disrupts currents that regulate global climate. The ocean isn't infinite. It has limits. We're pushing those limits. Marine ecosystems are unraveling. Fish populations are crashing. Plankton, the base of the ocean food web, are struggling. If the ocean fails, we fail. We depend on it for food, for oxygen, for climate regulation. Half the oxygen we breathe comes from ocean plankton. When we damage the ocean, we're damaging ourselves. Then there's the sixth mass extinction. We're in it now. Species are vanishing not from asteroids or volcanoes, but from habitat destruction, pollution, climate change, human activity. Every species lost is a thread pulled from the web of life. Ecosystems are resilient to a point, but redundancy has limits. Remove enough threads and the web collapses. We don't know where that point is. We won't know until we've crossed it. And once crossed, there's no going back. Extinction is permanent. The species we're losing took millions of years to evolve.